Today's episode of Binder Podcast is brought to you by the Columbia Museum of Art's 75th anniversary sponsors, including Art Angel sponsors Dominion Energy and Joyce Martin Hill, and cultural champion sponsors Abacus Planning Group, Blue Cross Blue Shield of South Carolina, Mr. and Mrs. David E. Dukes, First Citizens Bank, Quackenbush Architects and Planners, and Hannah and Ron Rogers. Thanks to them and all the CMA sponsors for supporting us on our 75th anniversary year. Let's start the show. You're listening to Binder. I'm Drew Barron. Hey y'all, producer Drew here. Welcome back to the Binder Podcast. It's been a while and it's exciting to be sitting here once again in the studio. I'm alone this week. Bray's gone. I'm very lonely and sad about it, but I'm actually not alone. I'm lying to you. I, of course, as always, have brought some wonderful guests to talk to you today about a really interesting subject. So listeners at home probably are well aware at this point, as I've said it ad nauseum, that we are under a lighting renovation. I think by the time this recording comes out, the downstairs will have reopened, but we'll be, construction's happening upstairs. All of our 20 galleries upstairs in the CMA collection are currently under renovation as we reinstall the lights and give you an opportunity to see art in a new way and also in a newly reinstalled way, as you probably learned in some of our previous episodes. And we're going to talk about that today, but not the same way we have been because, I don't want to bore you with the same old song and dance. And in fact, I think you're going to really enjoy our new dynamic for today because I have with me a wonderful first-time guest of the show who I've been working with all year long, Jackson Councilman. He is from our visitor experience department, but he does a lot more than that. And so tell us a little bit about yourself.
All righty. Thank you so much. Howdy, I'm Jackson Councilman. By the time this comes out, I will have graduated with a bachelor's in neuroscience with a concentration in cellular and molecular biology. And most of my key research area is in sensory systems and how we are able to perceive the world around us, and with a heavy focus on my end on vision. I do a lot of work with visual systems, how all that works. So yeah, that's my jam. I'm the vision guy.
Well, I hope that you can help all of us get a better perspective today then on this topic, because we're going to be talking about light and color and art and how these things work within our brain. And let's be honest, I'm no expert on this, so I'm so glad that you're here to help us out.
Thank you for having me.
We've talked a little bit before on the podcast, and if you know me, you've heard me go on and on about how light temperature is a thing. Light is measured in Kelvin, for those who don't know, in terms of the temperature, the color temperature of it. The best way to describe this is, have you ever gone into a room that was all just kind of those orangey, tungsten-y lights, and then walked immediately outside and everything looked blue for a second? That's because your eyes are kind of readjusting to the color temperature outside, right? Because it's like a slightly different hue. The sun is a little bluer than maybe a candlelight would be. So that is it on a very, very basic level. But to be honest, I don't really know what light is. Aside from what it does, I have no idea what it actually is. So I'm really hoping that you can explain to me, Jackson, what is light?
So, light is, first and foremost, extremely confusing.
This is starting off strong.
Always just a strange phenomena, and even stranger that we can sense it. So, light kind of acts as two different things at the same time. It's called wave-particle duality, and that just means that light acts both as a wave traveling through space, so it kind of oscillates, it's just kind of a force almost. But it also can act as a discrete particle, like what we call photons. And so that just means it can be like a finite, discrete packet of information. And so this dual nature is really strange, but at the same time, extremely useful and is part of the reason we can function in any way that we can today. So the nature of how light works is you take a light source, like a light bulb, a gallery light, anything like that. It'll beam light particles down onto whatever object it's pointed towards. those photons will then either be reflected or absorbed by that object. Now, everything we see is just the light that's being reflected from an object, which is strange to think about, that the green grass you see outside or the painting you see might not necessarily be that color. That's just the color that it's reflecting. It just absorbs everything else. It's extremely odd. But once that light is reflected out, it'll beam around, it can bounce, it can refract, but eventually it will enter your eye and hit the photoreceptive part of your eye called the retina. And on your retina, there are two different kinds of photoreceptors. And before I get to that, photoreceptors are just basically your body's way of capturing light. Once light enters your eye, it'll bounce around, hit the retina, and interact with one of these types of photoreceptors. And so photoreceptors, in the most basic sense, are almost like light switches. So light will interact with them, and there's a protein in every photoreceptor called an opsin that changes shape depending on what wavelength of light is hitting it. And so once you have that kind of change in shape, it again acts like a light switch and activates a nerve impulse. And so once you have enough impulse, once you have enough stimulation, you see an image, you get vision. It's a wild process. And so diving a little bit deeper into that, in human eyes at least, you can split photoreceptors into two kinds. There's rods and there's cones. So rods are your more sensitive photoreceptor. They kind of deal with your more peripheral vision. They're more for just saying, oh, there's an object in my field of view. I can sense something there. But your cones, on the other hand, are your more acuity focused. So they kind of deal with raising the resolution of your vision. They are kind of the reason we can see things in focus and detail and not in just a broad sense of pixels. And that kind of nature comes down to how they're wired. So rod receptors can operate in lower light conditions. It's a process called summation, where you take multiple rods and you wire them into the same interneuron. And so what that means is you can have a much dimmer light source, but since it's spread out over more of these, it takes less to get them to activate. So you get that raised sensitivity. But with your cone cells, they're more focused on acuity and resolution. So they are more wired like one-to-one for interneurons. And so you can think of that as allowing for pixels on a screen. So each cone, once it responds to a different wavelength of light, it'll ding a pixel. And so once you kind of have all of those in summation, you get this really detailed picture of the world that we can see now. So a really interesting thing about cones is they are the photoreceptor that's most responsible for our ability to see color.
Yeah, you brought up a couple of really interesting points there, and I did want to point a few things out. So a moment ago, you were talking about light absorption, right? Here at the museum, light absorption is something we're thinking about all the time, right? It's a conservation issue as well, because works can only take on certain amounts and intensities of light before it actually starts to damage the work. That's why works on paper can only be on view for a really short period of time before they have to rest in total darkness for multiple years, because they absorb light. If you've ever left like a photograph or a poster near a window for a few years, you know exactly what I'm talking about, because it just starts to fade. It's literally taking on that light and it's damaging like the inks and the paper itself over time. Another thought I had just now as you were talking about that, when you started talking about the human eye, is this concept of camera obscura. For anyone at home that has not heard of this, who didn't have a background in art history or photography or anything like that, camera obscura was originally kind of written about by Leonardo da Vinci, a technique that a lot of artists of that era ended up adopting. And essentially, it works the same way as if you've ever done a pinhole camera in an art class or something like that. It's working in a really similar way. So you create a box that's like sealed on all sides, and you put a very small hole in there. And what that does is it allows light to travel in and then reflects that light back out onto the wall, opposite end of where the hole is placed. What you end up seeing is you see essentially like a projection of what is outside of the box. And it's reversed and it's upside down. But the really interesting thing about this, the art historical moment, is like this is how they would draw from real life for many years before we had photography. And these principles would create photography later as well, obviously. And the best thing about this is I've always heard that in a lot of ways is sort of how the human eye intakes information as well. It's doing a really similar process. So like
it's almost exactly the same. Like
Yeah.
even down to the reversal of the image, when the light is projected onto the retina, the image is upside down. And later on in higher cognitive processes, your brain will flip that image to get it to be where it is. It's extremely fascinating. Now, the one key difference that I think points to kind of the interpretive nature of vision and art and everything in general is, while yes, you do have that image projected onto the retina, once you get higher up into the brain, those spaces on the retina aren't evenly represented.
Yeah.
So there's much more brain space dedicated to certain parts of vision. So your fovea is your kind of like your spotlight. That's where you're getting the highest acuity. That's where you're getting the highest amount of detail. And so obviously your brain dedicates the most space to the fovea. In doing that, this gets a little philosophical and more kind of experimental, but
that's what this show is all about, baby. Let's do it.
But once you get into that strange kind of transduction where it isn't necessarily just strictly physical representation, there's room for interpretation. There's room for different modifications to take place in the eye. It's almost like a painting. Like there is a level of interpretation and a level of abstraction that's done once you get into the higher order processes of things. That's extremely interesting. And it really calls into question, like, hey, me and Drew, are we seeing the exact same things in this room right now? There's really no way to tell. Because like once you get into color vision, which is a strange topic in and of itself, there's a lot of individual difference. There's a lot of wiggle room in there for different things to kind of arise and shape and change.
Yeah. So like, I mentioned at the top of the show, just kind of this like whole idea of like the color spectrum, right? Like I said, you can tell the difference when you're looking at a candle versus looking at the sun, though you shouldn't stare into the sun. I do not suggest that. Or really a candle for that matter. You probably should just not look into any direct light source for very long. But it goes a lot deeper than that. So like, I'd like to do a little experiment with you here, as it were, on this very scientific episode of Binder Podcast. I want to talk about a painting. It's a more or less recent acquisition. It's by Osamu Kobayashi. It's an abstract painting that we had on view before the collection came down. Some of you may have seen it. It was in Gallery 20 in the Modern Contemporary wing. It has just a handful of colors that are sort of like swirled and like spiraled together. And there's a lot of deep contrast in it, right? Like there's like a teal that's like outlined by a very thin yellow and then like a bursting like red and orange. Nothing is better audio than having a painting described to you. I know, but I really am trying to get to a point here. And that's that color is a wavelength in itself. Is that correct? Am I understanding that correctly? Can you sort of outline for us, and especially me, how all of this works and what's happening when we're like looking at a big, bright, colorful, abstract painting? Like, how are we seeing this?
One of the big influencers on how color is perceived are the different types of cones we have. So humans typically have 3 cones available to them.
Yeah.
So there is the short range cone, the middle range cone, and then the long range cone. And so these different lengths that we're talking about are the different wavelengths of light. And so color corresponds to a specific wavelength of light, with the shorter wavelengths being your more blue-violet tones, and then your longer wavelengths being your more yellowish-red tones. And so these different cones incorporate and absorb different wavelengths of light. It's almost like a color panel of once light hits the eye, these different cones will pick up on their various different wavelengths of light. They'll light up and respond. And so once you have this response from these cones, they undergo a process called opponency. And so opponency is really the basis of how we can see any kind of hue or any kind of like spectral detail of color. It's really fascinating. And so what happens is you take 2 cone types and you put them in opposition. So there's 2 main types of opponency humans appear to exhibit, and that is red-green opponency, where you take the middle and long range cones and then you subtract their effect. And that gives us the kind of like yellow to green gradients. That's how you can see your oranges, that kind of thing.
Yeah.
And then the other one is blue-yellow opponency. And you get that by taking the middle and long range cones and adding those two together and then subtracting that from the blue. And that gives us our kind of like violets to pinks to purplish kind of gradients. And so that kind of contributes to why the Kobayashi painting stands out as much as it does.
Yeah.
Is when you're comparing these kind of opposite ends of the spectrum, you're going to get a lot of distance between those two. And that distance translates to the striking contrast. They're different worlds in a way.
Yeah, no, I mean, I think, and we were talking off pod a little bit about like how this also affects things like people that have color blindness, right? Like because it is directly affected by like how your cones are able to intake these different wavelength spectrums, right? Can you explain that a little bit?
Of course, yeah. And so the way color blindness works is typically there is a type of cone that's non-functioning. It's usually on that receptor level, while there are cases of people who have it on the higher cognitive order. A lot of times that leads to like what some people think of as color blindness, like full monochrome vision. In reality, that's not really the case with most people. The more common form is red-green color blindness, where you have a missing either middle or long range cone. And so what that does is that kind of leads to a lack of being able to distinguish your like greens and your reds and that kind of thing. Most people describe that as seeing kind of like almost like a bluish yellow to green, just one single spectrum of hues. And while that does in our modern world lead to some issues of like seeing certain red hues like stoplights, that kind of thing, but in terms of the natural world, it's not necessarily that big of a detriment, because what you get when you have less types of cones is you get a sharper sense of contrast. And the reason that is because when you imagine your cones, think of it like 3 different buckets. So when light enters the eye, it has to fill these buckets to a certain point to activate.
Yeah.
So if you have a bunch of different cone types, you're splitting the water into a bunch of different buckets, meaning it's way harder to get them to the point of firing. But if you've only got 2, it takes way less to fill those buckets. And so you can see way sharper contrast between things. There's a lot of experiments done with different species of monkeys that there's actually a sex disparity between trichromatic and dichromatic vision in certain species of primates. And what that leads to through experimentation is the trichromatic monkeys, while they did have an easier time finding certain objects in a scene, they were worse at detecting, say, a bug sitting on a leaf than a dichromatic monkey. And that is because you're filtering so much more information. You're literally trying to find a needle in a haystack, where if you've got only 2 channels to go down, it's way easier to say, hey, this thing sticks out.
Yeah.
I'm gonna grab this bug. And so that kind of also leans into the kind of, this is getting a little bit out of my wheelhouse, but the interesting genetics behind vision, and specifically color vision. So the reason you see the sex disparity between these species of monkeys is typically your middle and long range cones are coded on your X chromosome. They're called like the sex-linked chromosomes. So they are subject to a lot more mutation and a lot more difference as lineages go on. As far as females typically go, it is 2 X chromosomes as opposed to an X chromosome and a Y chromosome. And so what that does is you have an extra X chromosome to tinker with.
Yeah.
There's room to kind of experiment. There's room to kind of grow in a way. And so what that can lead to, and kind of the way color vision arose in and of itself, is you had a mutation in the long range cone that shortened it and allowed it to respond to middle range lengths of light. And yeah, that kind of is what led to opponency in the way that we can imagine it now.
I remember you telling me off pod a story sort of related to this about Monet. And, you know, many of our listeners at home will probably remember our wonderful Monet painting that we have in our collection. It's more or less like a landscape impressionist painting. Lots of blues and greens and purples. It's a really beautiful work and a real showstopper, a fan favorite. But I feel like this little anecdote that you gave is not only a perfect example of this science directly affecting an artist's work, but also kind of feels like it's really directly affecting this specific painting. So can you tell me a little bit about Monet?
Of course, yeah. So Monet's a really interesting case. So he had a lens defect that prevented his lens from filtering out ultraviolet light.
I'm sorry, let me stop you right there. What is ultraviolet light?
So ultraviolet light, it sounds way cooler than it is. Ultraviolet light is basically wavelengths that are a bit shorter than are in the visual spectrum. They are ultraviolet. So they are very high energy particles because as you kind of get down to the smaller wavelengths, you're packing way more energy into a smaller unit. And UV light is everywhere. It's radiated from the sun. It's you see it in your UV indexes for tanning, anything like that. But the eye typically filters it out because it's not necessarily the most useful information for human eyes.
Yeah.
But in Monet's case, his lenses didn't do that. And so what you would see is the ultraviolet light that dipped more towards the visible side, once that reached his eye, that kind of left that like purplish hue to light. And that's why you see that kind of pervasive throughout his work. You really see him depicting light as this almost purple haze. Like it's very haunting in a way. Like it's amazing that there is this kind of force all around us constantly that we are completely unaware of. Now, some animals are aware of it. There's been a lot of work recently in birds being able to perceive ultraviolet light. They are considered tetrachromats. Certain species are considered tetrachromats. And what that leads to is they see the world in almost an order of magnitude of more contrast. Because you got to think, going from 2 color channels to 3, it doesn't sound like a lot, but when you really think about the practicalities of that, that adds a whole other spectrum. So it increases the magnitude, I believe, like 10 to 100 fold. And so you get that again once you incorporate ultraviolet light into the equation. And that's why you kind of see so much vibrancy in Monet's work, so much kind of almost alien color to everything.
Well, and you know what I love about this, Jackson, is that all the time on the show, we're always advocating for the fact that, like, everyone's going to see a piece of art differently. And now we haven't ever done it quite as literal as we are right now, but we're always talking about you're going to be bringing your own life experience, you're going to be bringing your own interest, you're going to be bringing your own background into any piece of art that you're seeing. But beyond that, also on a very literal level, everyone's going to see this painting differently because we're all seeing the like color spectrum slightly differently. Now, we can't necessarily probably know how differently, right? Like,
that's the interesting part of it, is there really is, I feel like people kind of have this idea of vision as a universal truth. Like everyone sees the same things. Like there's an objective way to see the desk in front of me. There's an objective way to see the walls around us. But in reality, there's a lot of interpretation done. Your brain does a lot of the legwork in kind of creating a visual scene. And so that leads to different effects. When you mentioned bringing people's past experiences, past thoughts and opinions into a scene, that's not just on the philosophical level. It really does reach into the physical. So once you kind of bring in these preconceived notions and things, they can affect your vision. From attention, which kind of determines what you see, whatever objects you're attending to or what you're going to see. And if you're not attending to them, you're not going to see them. But even deeper than that, there's differences potentially in how people perceive different hues of colors. A lot of it can come down to language. There's so much that influences it. There's an interesting story that I heard recently in a lecture about a tribe. Basically, they have less words for different colors. So they kind of categorize things into, I believe, 4 or 5 broad categories. And so what that leads to is there have been surveys done with them that they can distinguish different hues of greens and different hues of reds at an insanely higher level than you would typically imagine. And that just comes down to their brains are more attuned to kind of distinguishing between these hues of color. by like not splitting it into so many different channels, you can kind of tighten the focus and really pick into the fine details of things. So again, it's just an example of how insanely variable vision can be.
Yeah. It's funny, earlier we were talking about our brain being flipped, or our brain flipping images. And I feel like mine has been entirely flipped by this conversation. All of this has been really fascinating, Jackson. And it's like, I am so appreciative that you've taken the time to share your expertise in this.
Of course.
And I'm really excited to say that coming up later on the program, we're going to be talking to somebody who you also know very well, who you have helped bring onto this podcast. Can you give us a little bit of a little setup for who we're going to hear from here in a few minutes?
For sure. So Dr. Palomares is coming up. She has been an extreme influence on my kind of scientific career. I am beyond thankful to her for everything she's helped me with. She is a professor at the University of South Carolina, but also does research into perception and attention. That's her kind of key jam.
Well, I got to tell you, I'm really excited to speak to her. Once again, it's been such a pleasure talking to you today, Jackson. Thank you so much for coming on the podcast.
Of course. Thanks for having me on.
Yeah. Come back anytime, buddy.
Thank you. Thank you.
Jackson Councilman is a recent graduate from the University of South Carolina. At the time of this recording, he's completed his degree and is setting off for his next set of adventures. Coming up on the program,
visual artists and visual scientists pretty much have similar questions. It's just the approach is different.
Dr. Melanie Palomares, after this. Hey y'all, producer Drew here. When the Columbia Museum of Art began 75 years ago, it did more than just open its doors. It created opportunities, sparked conversations, broadened perspectives, and ignited moments of discovery through art. Over the years, we've expanded significantly, moving from the stately house on Senate Street to the iconic building on Main Street. The CMA isn't just a museum. It's a dynamic hub where art comes alive and everyone is invited to join the experience. But we can't do any of this without the support of our community. And a great way to show your support is by becoming a member of the Columbia Museum of Art. Not only will you receive great benefits like museum admission, early registration, and discounts, but your contribution will directly support initiatives at this museum, such as our public access days, educational programs, and so much more. You can learn more about CMA membership at columbiamuseum.org/belong. Help us continue to bring unforgettable creative experiences for all of the residents and visitors of South Carolina to enjoy for the next 75 years and beyond. columbiamuseum.org/belong. And now, back to the show.
Hi, I'm Dr. Melanie Palomares, and I am a faculty member in psychology at the University of South Carolina.
Welcome back to the podcast. I'm continuing to wade through waters that are just way outside of my depth. But, I think I brought a pretty powerful flotation device along with me for the second half of the show. As you might have heard earlier when we were talking to Jackson, he has been working with a professor over at the University of South Carolina for the last few years as an assistant. And somehow we have convinced her that it's a good idea to come here and talk to us today. I'd like to welcome to the show Dr. Melanie Palomares. Dr. Palomares, thank you so much for being here.
Glad to be here.
Yeah. So you teach at the University of South Carolina. Tell me a little bit about what you do and what you do in terms of your research.
Yeah, so I primarily teach undergraduates about the science of psychology. Now, you're probably saying, psychology, is that a science? Well, I'm saying yes. My specialty is really on cognition, particularly visual spatial cognition. As a teacher and as a researcher, you always have to be willing to learn and, on occasion, be wrong. And that's, I think, really important for everyone to be comfortable with. And so that's what I'd like to impart on all of my students in the
Yeah.
lab or in the classroom. It's like, keep on learning, and it's okay to be wrong. That's how it goes.
What are some of those kind of common misconceptions that maybe you've run across?
Ooh, common misconceptions. Where do I begin? I have to like rummage through in terms of like the biases that we have. So one of the things that's been popularized, the Stanford prison experiment.
I've heard
You've
of
heard
it.
of that?
Yeah.
In this particular study, people were asked to role play as prisoners and as guards,
Right.
right? And it was pretty dramatic. It's like, oh my gosh, in like, a few days, you could make people act so inhumanely. And I think, we are really hoping to kind of find that because some of the grotesque things that humans do, but we found out that a lot of the students made up their stories to fit the hypothesis
Mm.
of the researchers, which is unfortunate because what happens when you figure that out is that it pretty much contaminates the trust in science and in psychology in particular. Because a lot of the comments that you see or hear in psychology is that, oh, psychology is just so intuitive and it's just a pseudoscience. And so you need people's trust
Yeah.
to, have them kind of like understand and to really take on like what we're saying. So it's unfortunate. So that was like a big thing. But in general, there's like lots more other little bits,
Bits for another podcast.
Yeah,
Yeah.
we can go on.
Yeah. I wonder though if that like when you talk about doing an experiment and you're going to have human subjects, right? Like I wonder if that bias is a challenge. Like how do you approach like getting around that challenge?
Very good question.
Yeah.
So you have to be clever. You have to be clever in not divulging from the get-go what your hypothesis is.
Yeah.
And so in cognition, it's a little bit different because we interface with machines. We have computer programs. We program like very simple video games, and we have participants, play this video game. So it's not like an interaction with the experimenter or the research assistant or anything like that. With that, you minimize sort of like these human cues, like, I really want you to do this, right? But even with a computerized video game, you have to kind of like be clever and in kind of like masking what you actually intend. So it has to be as neutral as possible. The language has to be neutral. It's like, we're just looking for your reaction.
Right. And you don't like lead like a certain result by
Right.
mistake.
Yeah. So you really have to kind of be clever and be scripted. Like you have to have a script, what you say to the participant.
When I originally kind of chatted with Jackson, and we preambled this at the first part of this episode, but Jackson just came in to intern with me for a few months while the building was closed, and we were just talking one day. So this really just came. It was just a kismet moment where I was like, "Well, what do you do when you're not here?" And he told me all about the work that y'all are doing there, and I was like, "Man, I have always wanted to understand." When I look at a painting, like, how does my brain understand what this is, And he was like, oh, well, like, there, and he went on and on about all these like different methods and mechanics that go on. And I was like, okay, this is going over my head. So let's take it a step back. And you know what? Let's just make a whole episode of the podcast about this because I think other people would find this interesting too. And so far, it's been great. And honestly, it's pushed me to do some of my own research on the subject. And I've learned a little bit. I'm hoping I'll learn a little bit more today. But I think that the folks at home are going to find this really fascinating. I know I did. It's really made me reconsider how I have approached looking at art at times. So
yeah, that's actually like the philosophy that I take. So I think that visual artists and visual scientists pretty much have similar questions. It's just the approach is different.
How so?
Well, I discovered this when I was a research assistant myself as an undergraduate. And I was in a lab with Dennis Pelly at NYU. And he put on an exhibit. And he invited artists as well as visual scientists to create art and to display it. And when you have this display, you couldn't tell which pieces are from artists and which pieces are from scientists.
Yeah.
Yeah. So in terms of like visual scientists, you want to know the limits of vision. You want to know perhaps like how they react, in the aesthetics, or what they see, what they pay attention to, how they switch attention and things like that. We have metrics for that, like reaction time or accuracy. But, artists play around too. Like they have these series where they change one thing, they're independent variable, but they don't ask explicitly. They don't ask the viewer explicitly, well, how fast do you do this? They just show it and then have the observer, the viewer, kind of like feel that themselves without explicitly saying it. So I thought that was really like eye-opening for me when I was an undergraduate.
I love that correlation, and like I've always believed that like to be like great at any kind of like skill set like that, you could be a scientist or a chef, or it's thinking creatively that gets you there, right? And so I can see how there would be a lot of that translation between these different practices. So I'm going to do a little experiment here, and I'm going to present you with an idea, and I just want you to help me sort of like get to that next step. So as listeners heard earlier, Jackson was sort of explaining a little bit of the mechanics of the eye and how we perceive color, and it was very fascinating. But I want to go beyond that, right? So once we get beyond the eye, where are we going? The example I'm going to give is, let's take a very vibrant still life, right? And it's just full of colorful flowers. Maybe there's like a vase and a table. And so if I'm looking at this painting, how am I making sense of it when it gets past that? Like, how do I understand that what I'm looking at, especially if it's not a physical table, it's not a physical vase, and it's not physical flowers, like what's going on in my brain that's making me understand what it is that I'm actually seeing?
Well, it is true that this is part of perception. It is happening in the brain proper. So after you sense the light energy around you, right?
Yeah.
So, light is made out of wavelengths, and you have different wavelengths, and wavelengths like determine color, right? So you have that information, and that is happening in the retina,
Right.
the back of your eye. And then you have then these projections from your retina through your optic nerves to the thalamus. So this is basically like, if you look at your brain, and it's like spherical, it's like the very core, the very center. That is your thalamus, and that is your sensory gateway. So your visual information goes to the thalamus, your auditory information goes to the thalamus because it's at the center. Okay? Makes sense. And then after the thalamus, it goes to the back of your brain, and that is your occipital lobe, and that is your visual center. But it doesn't end there. After that, it basically goes all over your brain. And we are such visual creatures. They estimate like 66 to 75% of our brain is dedicated to some sort of visual processing. Now, when it comes to this still life that you're talking about, it's actually like so you need to imagine yourself. If you close your eyes, there's darkness. And when you open your eyes, you immediately get the sense of this picture, right? And so just from like light energy, it's just energy, you get this perception of flowers or vase or whatever. And the way that our brain does that cleverly is a sort of like a strategy of divide and conquer. You basically have these neurons from light energy, and they kind of like transduce that into these neural signals. And these neural signals have different sort of like math. Different cells have different math, like of decomposing this image, and then in the brain proper, you put them all back together again.
So when Jackson was naming some potential experiments that might be a good example to bring in. One that he kept coming back to was the Hubble and Weisel.
Hubel and Wiesel.
Oh, it's Hubel and
Wiesel,
Weasel.
yeah.
Oh, that's way better than the way I was reading it. I do want to go ahead and address the elephant in the room to listeners at home. If you don't like the idea of animals being experimented on, you may want to skip forward just a minute or two. Remember, this was a different time. I guess I'll leave it at that. But I do think it's relevant to understanding some of this to talk about that. So I would love for you to explain to me what this experiment was and what it kind of taught us about perception.
Well, Hubel and Wiesel won a Nobel Prize for this. And this Nobel Prize was basically because it was an accident. So I love this story because it's about the serendipity that's sometimes necessary in some scientific discoveries. It's like, oh my gosh, it's like an accident. So Hubel and Wiesel were physiologists, neurophysiologists, and around that time, they were figuring out what parts of the brain does in terms of the visual system. Before they were doing this experiment in visual cortex, which is the occipital lobe in the very back of your head, right? So the occipital lobe is like if you touch the back of your head, that's where your visual centers are, right? They were experimenting, showing anesthetized cats pictures while they were recording with an electrode. So what they do is they perform surgery and they put an electrode by the occipital lobe and they see what happens when the cat is seeing some sort of stimulus, right? So when they were starting out, they were showing just light, like a spot of light, a circle, spot of light, and nothing. They were not getting any signal. Spot of light, nothing, nothing, nothing. And I'm like, oh my gosh, this is not working. It should work. Other people have seen this in the thalamus, the lateral geniculate nucleus. So what's happening here? Like, how come something's wrong? And what ended up happening was that in the process of changing the slides, because back then, you show pictures on projectors.
Yeah.
Right. And so you kind of physically slide out your picture. They heard the neurons fire. So what do I mean by neurons firing? So they're clever enough to hook up their machines to speakers. And
oh, wow.
and
really?
Yeah.
So you're talking about literally hearing it.
Like literally hearing neurons pop. Yeah. So when neurons fire, it's actually a waveform. So when you hear a spike, it sounds like a pop. And then if you look at oscilloscope, you see the waveforms on this green monitor.
Right.
Right. So they see this, but because it's really hard for them to kind of pay attention visually, they put in a speaker so that they can hear it. It kind of makes sense, right? To signal to them oh, something's happening. So what happens is when they slip this slide, they heard it pop. So what's going on there? The neurons in the visual cortex, when they're recording, is not really interested in static dots. They might be interested in something that moves. They might be interested in a line rather than dots. So that's amazing that it's that's the lore, right? That's the accident. And then it's okay, what if this is true? What if the visual system is hierarchical in that when you're in the retina, it's just you deal with light energy. When you're in the thalamus, you're actually dealing with contrast. So the difference between light and dark, but they're still circular. And when you are in the visual cortex in the occipital lobe, then you have more complicated stimuli like lines. So imagine if you line up a bunch of dots, it looks like that's what it's doing. And so now you're detecting orientation. And so that's what they did. Hubel and Wiesel basically systematically changed the location of the electrodes and mapped out the primary visual cortex. And they found that certain cells have selectivity for vertical lines and then some diagonal lines, some diagonal line. I mean, basically it's mapping out visual stimuli
Yeah.
out in the world, and it's mapping it in your brain. And it's not just orientation. They looked at, sort of like color. They looked at motion, if it's moving or not. They looked at like depth, because we have two eyes. How do you? So they did a whole bunch of experiments that basically tells us how the visual system first segments the picture out there in the world, cuts it up basically, and it has a map of that cutout features.
And then makes sense of it again.
Yeah, and makes sense of it again. So that's just the primary visual cortex. We call that V1, right? V1, because it's the first visual cortex, so it's V. And then you go to like V2, V3, V4, and so forth, and you have all these other areas that people have mapped out. And so they found that there are certain parts of the brain that is specialized for certain things. So for instance, when I say V4, you say that's visual cortex 4, right? That is specializing in color. So the color information, like goes there, right? But they've also kind of looked at form, like curvature or like simple shapes, and that's V4. Now, if you look at V5, what do you think?
It's going to be one step above 4.
But...
You put me on the spot.
Now you can guess. Hypothesize.
Well, let's see. If V4 is thinking about color and it's thinking about shape and line, V5 is that wouldn't be texture. That's silly. What is it?
It's actually like a different type of information. It's for motion. So V4 is for color and shape. V5 is for motion. And you could imagine like what happens if you damage that, right? So if you damage the V4 area, you won't be able to see color. It actually has happened. And then same thing with MT. Imagine if that is lesioned out or got damaged, then you won't see motion. It's like stop action.
So everything would just be kind of like a stilted.
Yeah. Isn't that amazing?
That is amazing.
Yeah. So the story is that the visual system decomposes these elements. That's the work of Hubel and Wiesel. And then other scientists have looked at other areas. And we have areas especially for faces, for instance. That's the fusiform face area. So in this area, which is like the bottom of the brain, it likes faces. So you show faces, and then the neurons there kind of light up, right? For objects, you have the inferotemporal cortex, like on the side, so certain objects and maybe certain textures. But, this is what we know now, right? But I'm pretty sure that they're going to figure something out what other, computations that these areas are doing. And we're still trying to figure out how they work together.
Yeah.
Right? So it's not just these areas working in isolation. They're working together, kind of changing up the weights so that, you make sense of like what you see out there. And that's where we're at. Like, how do they kind of communicate to each other, and how does that change over time?
Yeah. Well, yeah, and I mean, I'm sitting here across from you, and everyone at home should know what a wonderful hand talker
I am.
Melanie
This is what I do.
And I wish you could have seen all the visual representation she was giving me just now during that. But I mean, that's a perfect example of like, I can understand that your arm has a certain shape and a certain color, but in order for that motion to work with that, like these things have to come back together somewhere, right? Like, and so I love that that's still like kind of an evolving understanding that is still sort of being worked out.
Oh, yeah. Like, so when it comes to perception, that we're just talking about like, how energy gets interpreted into these things. But that's just what we call bottom-up information. Bottom-up meaning, coming from your environment. That's it. Along with bottom-up, you have top-down information. And top-down information is basically what you as a person brings to the table. Your brain has had experience and your history and, everything else that you've learned from the past. And that is your top-down information. And together you have your perception, You interpret the world and then make decisions based on that. So for instance, like here in the United States, traffic signals, right? You have red, green, and yellow. And these are colors with significance, because if you drive and it's red light, that means you might get into an accident. There's like consequences. But imagine, so you're perhaps as a person doing this and you're driving, you're always like paying attention to what's green, what's red, what's yellow, whatever, right? But imagine if there is a culture somewhere, they don't have these signals. They don't even drive, let's say.
Right.
They wouldn't have the same significance, and maybe they don't pay attention to these things as much as we do.
So, I love that you brought up movement a moment ago, because I think that's actually a really nice transition to sort of talk about another subject. And I'm going to bring some art back into this conversation. And so I was looking at pieces within our own collection, kind of thinking about some of the ideas that I knew we'd be talking about today. And one piece that's a personal favorite of mine actually really stood out. And it's called Blue Dominance. It's by Bridget Riley. She was an op artist. The op artists, like, very famously, they love to make these like kind of very simplistic patterns that when you looked at them, it almost looked like they were moving, right? And because of like the tight knit pattern or just other kind of like visual effects. I mean, op art literally means optical art, right? And I've always loved that stuff. I'm a big nerd for it. But what I didn't know was kind of the psychology behind how that works until I was doing a little bit of research. And I was reading up on Gestalt. Did I say that right? Psychology. And, I think some people might have seen like the Rubin vase illusion. It's really famous with the two faces. That also is a vase, depending on which way you look at it. So can you talk to me a little bit about how that actually works and just like what is Gestalt psychology in general?
It started in Germany in like the early like 1900s and 30s. And you have a group of these philosophers, psychologists, kind of, they're really big into phenomenology, and they're trying to kind of explain the world as a holistic pattern, so a holistic perception. The principle is that the whole is greater than its parts, meaning that, the forest is not simply like a collection of trees. It's something else in its entirety.
It is a forest.
It is a forest, in addition to like the collection of trees. One of the Gestaltists that's like very prominent in my head is Wertheimer. And he was the one who drew out, he has like in his book, I have this in my office, like he drew out like dots that's grouped together. So he had this Gestalt laws. And so he was looking for these laws or principles of grouping. Like, how do we group things together? So he said, like things that are close together get grouped together. Things that are lined up get grouped together. Things that are similar get grouped together. Things that move, And so are the Gestalt laws. And what I like about that is that, it's describing something. And then in the 90s, people started making measurements, like psychophysical measurements based on the Gestalt principles. And so even though it's like, oh yeah, this is what you experience, but now we have the language and so like the methodology to kind of like explore what's happening with Gestalt. So basically it's like your holistic perception, right? Meaning that your own perspective, your own like experiences are kind of grouped with the stimuli, the physics of the world. And then so you do that and you interpret the world with that in mind, like all together with your own experience and with what is being detected by your visual system. And that's essentially what Gestalt is in terms of like this organizing principle. I think that's the big thing about them is how we organize, prioritize what we see.
Yeah.
Right.
And my understanding, and please correct me if I'm wrong, because I'm sure that I am, is that like when like op artists and other people were playing around with these ideas, they were playing with what's called like figure ground dissonance. Can you explain to our audiences kind of what that means? And like, once again, audience, like picture that vase with the two faces in your mind. I think that will be really helpful here.
So when we say figure ground, this was actually really big with the op art stuff, but also in computer vision back in the day, because everything is like, new with computing and like, how do you present a digital image? I mean, this is exactly like the same questions from these artists and from these computer scientists. And so figure is the object, like the object in front of you. Ground is the background. That's all it is, right? An object is the figure, ground is the background. And when you are walking around in the physical world, you see, aha, there's a ball on the floor. The ball is spherical. It has, light. It changes in, color. And so you know that the ball is separate from the floor, right? And we make an assumption that the ball is solid and the floor is flat, as opposed to like the ball is a hole.
Yeah.
Right? So the ball is the figure rather than the ground. But if you interpret it as the ball, there's something circular as a whole, then it's the opposite. It's really a depth cue. Now, with Bridget Riley stuff, I love her stuff because it has a lot of textures, but she plays around with depth because of curvature. Because of our experiences in the world, we basically learned that there are certain constants, right? So where is light usually coming from?
A light source.
A light source, which is from the
top.
From the top, because the sun is from the top.
Right.
Right. And so we made our world, when we go into these buildings, the light source being on the top usually. There's your ambient light, right?
Right.
But then we can be clever with other lighting. But typically, it's the light is coming from the ceiling.
Yeah, it'd be pretty disorienting if we only lit the floors.
Yes, right? Like for Halloween, right? The flashlight from the bottom like makes you look scary, right? Based on this, like these previous experiences, we make assumptions of like, oh, it makes sense that is a sphere, that is a ball and not a hole, even though it's circular. The really cool thing about these op art is like they're trying to investigate the mechanism or investigate the process of how we see depth, for instance, without really these psychophysical experiments, but they're doing the same thing. Like, how curvy should this be? How wide should this be? Experiments in in vision science, we do the same thing. Like, we make changes in width, we make changes in luminance and color and things like that, and then see what the reaction is. So in a lot of her work, you have these waveforms, right? These patterns. So it kind of mimics a flow, right? So think about like lava, like, or even like textiles, togas, And so if you look at those types of textures, like even here, like this
She's pointing at a curtain.
Yeah, is hanging, and it has pleats. And I'm interpreting the pleats as going, like closer to you or away from you.
Creating depth.
Depth. But they're just differences in luminance, in color, or whatever, based on the light source, which is not from above, but I can see where the light source is, right? You can actually triangulate where the light source is based on the object. So if you want people to see depth without any like figure that could bias you, I assume that's what you would get with this picture of like the waveform and changing color. And it's actually very beautiful. I love her stuff.
I love her stuff too.
Yeah.
I'm a huge fan. What I think is interesting about a lot of this is like something we often talk about on the show that we've talked about with many, many guests, and I'm sure all of our listeners are tired of hearing me say this, but when you look at a piece of art, you're not just bringing the knowledge that you have about the artist or whatever. Like, you're bringing your own personal experience and your own personal background into that piece, right? Mm-hmm. And then that's helping inform the way that you actually see the work, right? Mm-hmm. And what I thought was really interesting when I was like reading up on this was I was like, well, and also literally, like, your past experiences are like a big part of what allows you to understand what it is that you're looking at.
when I'm looking at, say, that vase and table earlier, right? If I'd never experienced a vase and a table, that might color my view of what it is I'm looking at quite a bit.
True.
You know?
So you distinctly said, like your language says, it's distinctly a vase and a table. They're two objects. But if you've never seen that before, perhaps you might say, oh, it's just one big piece.
Right.
Right.
Yeah.
So scene segmentation is something that vision scientists have looked at a lot because of computer vision. And so it actually led to that, and now AI, it's actually like it goes hand in hand. It's like, how do you know what an object is? It's the same idea with like, how do you know what a chair is?
Right.
How do you know what an object is? What is an object? And there is still no satisfying like one definition of what an object is. Well, how do you determine what a feature is versus an object? What is a feature was an object? Those are still kind of like ambiguous things, right? But our experiences in the past tells us, that is an object, that's another object. And you could imagine yourself, like, this thought experiment. Imagine if you haven't experienced anything visual and then suddenly you were given sight.
Yeah.
Right? Like, how would you experience that? So, as a kid growing up, you didn't have vision. And then now that you're an adult, you're like, oh, you're seeing. Like, will they interpret the world in the same way? Initially, no, but then with experience.
I was like, is this one of those, I have to answer that question? Because I have no idea.
There's actually like a study. It's like Project Prakash over at people from MIT. If a person born blind, will they be able to like understand that a sphere and a cube are different just by sight? And the answer, I think, there are some people with cataracts in India.
Yeah.
And so they gave them cataract surgery, and they actually were able to kind of make some measurements, and they found out that, they had a really hard time in the beginning to figure out like a sphere and a cube, but then over time that they were able to. So it's actually kind of cool.
And this is why every baby looks so amazed by everything that they see.
Oh, yeah. Developmental studies are actually pretty cool.
Yeah. So I have one other kind of subject I sort of want to talk to you about today. And it also relates to something that we say a lot on the podcast. So I'm a big advocate for slow looking at art. There's been a lot of studies as to like how long a general visitor might spend with any given work of art. And the answer is not long enough. Because, you can look at a painting and like, I'm just going to keep using the example of a still life painting because it's easy. But like, if I look at a still life painting, I may notice right away, okay, once again, there's a flower, there's a vase, there's a table. I've seen it. I walk away, but like what you've missed is all of the like detail and all of the choices, right, that this artist has made to make that flower and vase and table. And I mean, that I think is robbing you of the experience of like really like starting to get to know the art in a more intimate way. And I understand that one of the things that you study is visual attention. And I felt like this was like a really nice correlation in the idea that like, obviously there might be some, I guess, evolutionary advantages to certain things about visual attention, right? Like, I think Jackson had given me the example when we had spoken of seeing a bright red apple and like in a green tree, being able to pick out that apple to eat it is an advantage, right? Like, because I don't need to eat the leaves, I need to eat the apple. So like being able to like make that the focus seems really important. But when we think about attention and vision, are like there ways that we can like play around with that for ourselves to like maybe be able to focus on other details, if that makes sense? And so like there's a two-part question. Really, the first part is really just sort of what is visual attention and like how does it work? And then beyond that, like, do you have any tips for listeners who maybe want to like test their visual attention?
Wow. So attention is basically the gateway to perception. That's it. So if you're not paying attention, you'll miss it. Right. And a lot of times we do because we're always in a rush or, we're looking at our phones or whatever. But people have been talking about attention for a very long time. So even like the first laboratories in the United States, they were like talking about attention. That's William James kind of stuff. Like, and even he said like, well, everybody knows what attention is. But really, we don't know what attention is. So attention to me is basically selectivity. So it's like picking out the signal in the noise. That's one type of attention, is like that selective attention. The other type of attention that you want to say is this sustained attention. So when you're like, I'm going to, saying that I'm going to focus on this, and you do that and you focus, you don't get distracted, right? But basically it is like this selectivity in space and in time. And so selectivity is a combination of, again, top down and bottom up, right? So bottom up, if something is like screaming at you, flashing at you, like really loud, you're like, oops, that's I'm going to focus on that. And our sensory systems actually are attracted to novel things that pop out, right? Because it's new, and you want to know that if something is different, is it safe, right? And then the other thing is the top-down information. It's like, okay, I'm paying attention to this big, bright thing. Is it really something that I want to pay attention to? So it's like, oh, okay, then now I'm going to use my top-down information, say, let me switch back to, like the thing that I was looking for.
Mm-hmm.
So I always talk about this, like my kids always have like unpaired socks. And it's like, because the room's messy, right? And it's like, oh, like I'm looking for my sock. I want to wear my pink sock or whatever. It's like, so you're looking for something pink. You should like look for something pink. That is, you focus your attention, your top-down information for that pink something or whatever, right? So you're looking for a pink sock and you're distracted by other pink things like pink shorts, pink flat, whatever, right? But you're still looking at that. So that's your attention. That's your top-down attention telling you like, look for something pink. And then the bottom-up attention might be like, oh, here's a book that I haven't seen in forever. So let me like go through my book.
You've just perfectly described me looking for a sock.
And it's just like, no, you look for your sock. And so your bottom-up attention is like, oops, squirrel, whatever, like capturing your attention. And then your top-down is like, I need to focus on this.
Yeah.
And every single thing that we do when we walk around is basically like these competition of our attention, right?
Right.
So we need that energy, that will to kind of focus on what you need to focus on. But it's getting harder, right? Because we're like zooming, and we have a very, very kind of fun computer in our pockets, like our phones. And so even when you're like waiting for somebody, you don't just like look around and observe. We're like scrolling on our phones. And so we're really hijacking our attention span because we're just used to like, we feel like if we're not doing this, like we're quote unquote bored. But one way that you to kind of like slow down, that you're talking about slow looking, is to actually practice it, mindful slow looking. Mm-hmm. So what I liked about my undergraduates, I miss undergraduates, but at NYU, is that my advisor at that time, my undergraduate advisor, Dennis Pelly, we used to go to museums and we would just kind of like look and observe, right? And that slows things down. Now, mind you, we didn't really have phones back then. Well, we did, but not like to the same degree. But it's still sort of like forcing yourself to slow down. And so people watching, we love people watching, I hope, still, right? Now, I see fewer and fewer people doing that, sort of like, let's say going to a park and sort of like having a conversation with a friend or whatever and just like looking at people walking or whatever. We don't do that. We're basically like on our phones. Mm-hmm. Like, so we really need to practice slowing down and saying that it's okay that I don't have my phone with me. It's good to slow down, but it is hard to do that. And you need effort to slow down now.
Yeah.
Like it's the opposite. Like before it was like, it's an effort to kind of like get going, but now it's like an effort to like,
and like,
stay still.
And I think artists, like they love to play around with that. I provided an example
of a piece of art that we have in our collection called the decoy. So in this painting, the first thing that will probably catch your eye is the striking figure of a woman in a headpiece that is maybe a little out of fashion today. Sort of looks like it might have been in Bram Stoker's Dracula, but like it's lovely, and like she has this like great kind of fleur-de-lis dress on. And then on the bottom right, and it doesn't really show as well in this printout, but there's a bright red rose. And so those are the first things you're going to catch your eye, right? But like, if you remember, the title of this is The Decoy. If you look into the shadows, you'll see a gentleman with a knife, right? And like, that's the idea, right? It's what you immediately pay attention to versus what you should like see just around the corner, right? So like, immediately when I started thinking about like this whole like visual attention and like what it is we see and why we see it, right? Like, obviously our eyes are going to be driven to that red rose because it's a bright red color in there, and like, we've trained ourselves to like look at the brightest thing first, right? And so I love that, like, even before a lot of this was probably written down, you know, like artists were already playing with these ideas and having an understanding of like where our attention lives.
Yeah. So, top down, bottom up. It's always those two. So big things, bright things. And if you look at the painting, you have a lot of dark spots on the, so like the background's very dark. And the lightest part is like at the center of the frame, which makes sense. Your eye lands mostly towards the center. She is the biggest form there. So you're like, oh, okay, what is this painting about? Like, it's called The Decoy. Why is it the decoy? So you're the woman, perhaps even the flower, but it's smaller, right? So it's the woman first and then the flower. So your bottom up attention goes to the figure, and faces are actually very salient to human beings. Like, we pay attention to faces. That's why we see faces in like everything, like clouds and like, like,
what is that pareidolia? Yeah.
So we have like, it's like where, everything has a face, right? And if you put a face on anything, you gravitate towards that. That's why you have a lot of logos and, with faces and, but so you gravitate towards that. And then, so that's your bottom up attention. Sort of like, oh, it's a face, whatever. It's bright. It's like, oh, so, and then you sort of like, well, it's called a decoy for a reason, right? That's what you were saying. So what is it about this painting? What is the intention of the artist? Why did this artist like name it decoy instead of like woman with a big hat or something like that? Right. So it's something else. There's a hidden meaning, a hidden intention that the title gives you, and that is the top-down information that the artist wants you to kind of focus on. Ideally, you would search like in that painting of what other things, so besides like the dark background, and eventually you see the other figure hidden with a knife.
Yeah. I feel like we could talk about this all day and go down a million different rabbit holes. And I would love to do that. We should definitely have you back on the podcast sometime soon to talk even more about this. And I hope that everyone at home has been paying attention and has made it here and was mindful enough to stick around with us to the end of the program today. But I did want to give you an opportunity. I know that you are actively doing research now, and I'd love to hear a little bit about it. You want to tell us a little bit about what you are doing today, and if there's any way people could learn more about your work or anything like that.
Yeah, so I'm actually very, very excited. This is a project with Jackson, and I don't know if he's mentioned it. We are studying scallops and what they see. So this is in collaboration with Dan Spicer in biology at USC, and he is the expert on scallop and scallop vision. And scallops have hundreds of eyes. Crazy, right? They have eyes.
You've unlocked a new nightmare for me.
No, but they're beautiful. They're blue eyes with these base scallops, and so you wonder, like, wait, why do they need eyes?
Yeah.
Like, what is it for? What do they see? What are the limits of their vision? And we're doing psychophysics with scallops and really excited about that. So that's like the new thing, because it's very different. I don't study scallops, I eat them. So, so that's one. And then the other one is in human psychophysics, I'm working with new students because Jackson graduated, and we're following up on his project on how we have these illusions of space and size. So a lot of times, and we talked about this, like when we see the world, we have these background and we interpret the world based on our background.
Yeah.
And a lot of times we're wrong because we're susceptible to these illusions, right? So the physical world is different from your perception. And so we're going to continuing on with that in terms of like these illusions of size. So how big something is, and we're definitely wrong in estimating the size of things.
Well, I'm going to have you back when we have some really big art and get you to guess what size it is.
That's fun for your campers, actually.
Oh, you know it. They love to tell me exactly what size they think it is. But Melanie, Dr. Palomares, however you would prefer to be called, thank you so much for being here. This has been really enlightening. Thank you for helping me navigate through a subject that I found very difficult to talk about, but like you made it so easy. So thank you again.
Yeah, thank you. It was a pleasure.
Dr. Melanie Palomares is a psychology professor at the McCausland College of Arts and Sciences at the University of South Carolina. Her research interests include visual perception and attentional selection, perceptual organization, and visual development in children. She's a lover of art and museums. And this fall, she'll combine these interests for her special topics course, Psych 589, Psychological Science of Visual Art. When I first started working at the CMA in 2014, a big initiative for education was, and arguably still is today, STEM. Sure, a lot of you are already pretty familiar with this acronym, but a variation of it I started hearing at the museum was STEAM: science, technology, engineering, art, and math. It actually makes a lot of sense if you think about it. The arts encourage people to think creatively, and that creativity is what fuels innovation in all of those fields. I believe that to do good work in anything, you have to start with the same question: what if? What if I try to throw paint at the canvas instead of applying it with a brush? What if a bridge could give you the experience of floating in the sky? What if it isn't just seeing light, but it's seeing it move that makes the synapses in our brain activate? So whether you're a painter, an architect, neuroscientist, I hope you never stop asking what if, and keep thinking creatively. You've been listening to Binder, a production of the Columbia Museum of Art. Today's episode was hosted, produced, and edited by me, Drew Barron. Research and editing assistance provided by Jackson Councilman. Special assistance from Joelle Ryan Cook. If you'd like to learn more about the podcast and CMA exhibitions and programs, visit our website, columbiamuseum.org.